Last lecture we have discussed exclusive OR gate, and its implementation using your NAND gates, NOR gates and all. Let us see a few questions on this lecture. Write down. Implement the following functions. One second. Write down. To implement the following functions. Determine the minimum number of two input to implement the following functions. Determine the minimum number of two input NAND gates required. Let us see. This is what we had discussed in the last class. Up to this, okay, implementation of XOR, XNOR we have seen using minimum. Now let us take a two different function and try it. Right. See here. Let us take the question. Right. These are the four equations given. What we need to do? We need to find how many NAND gates are required minimum to make these functions. Right. Here, let us start with the first one. Here I will give you one shortcut possibility. Let us use that. First, before that, conventionally how we do? You need A, B, C. Na? First take A and B. Connect to NAND gate. I'll get AB bar. This you connect to one inverter. That is also using NAND gate. Then AB bar whole bar. AB bar whole bar is nothing but AB. Now take C. And this you connect to one NAND gate. Then AB bar whole bar into this input C whole bar. Now take one inverter here. Then what is the answer? AB double bar into C bar is the input, is the whole bar. Now you can understand here, double bar cancels. What is the answer? I will be having A, B, C. So how many gates are required? 1, 2, 3, 4. So I can say minimum gates required is 4. But instead of doing this much, I will show you easily how to do it is. How many bars are present here? 1, 2, 3, 4. So blindly number of bars will tell you number of gates. Every time you have a gate here, you are getting one bar here. So in the function itself, if you are able to find the number of bars required, it will say you number of gates required very easily. I will show you here. Suppose this is the answer question. AB, CD. How to make ABCD? For getting AB, I need 2 bars. For getting AB, I need 2 bars. For getting CD, I need 2 bars. For getting AB into CD, I need 2 more bars. So, for getting AB, 2 bars. For getting CD, 2 bars. For getting AB into CD, 2 more bars. Total how many? 6. Minimum 6 are required. 1, 2, 3, 4, 5, 6. Okay. Or you can see generalized answer also. Suppose you want n input AND gate. It requires 2n minus 2. 2 input NAND gates. Here how many inputs? 1, 2, 3, 4. Na? 2 4s how much? 8 minus 2. 6 NAND gates are required. Here 3 input. It is only for AND gate. Okay. 3 input AND gate means 2 3 is 6. 6 minus 2 4 is required. If you want NAND, one bar is already present, no need to have second bar, or you can say the answer will be in this case may 3, in this case it will be 5. If you want NAND gate, that is, if you want ABCD whole bar, answer is only 5 gates are sufficient, no need to have 6 gates in that case. Now come to this. This technique is applicable only when your function is of form, product form only. Okay, otherwise you cannot apply this technique. First, any function convert into product form, then only you can apply it. Now, A, B bar, C. You can write it as AC into B bar. A, B bar, C, you can write it as C, you keep it here, AC into B bar. Now, you understand here, it is of product form only. Why I keep B outside means because if bar is in between A here, C here, it will make it complex. So make AC one side, B bar one side. Now take bars. Here double bar. That is AC bar, whole bar is AC. B bar is one bar. Next, this into this means 2 bars are required because NAND gate we are doing. This into this whole bar will come with one NAND gate. Another bar will come with another NAND gate. Without that, you cannot make the product. So how many gates are required here? 1, 2, 3, 4, 5. Here how many bars will tell you number of gates required. Is it clear? Same technique you can apply for any product function. Okay. For XOR and XNOR, I have already given you the shortcut answer for implementation of NAND gates. If the product is given like this, there is another case what we call it as AND OR function. Just next I will discuss in the 2-level logic. We can also use that concept also later. Okay, for continuity, if it is a product part, always you can use this one. Now, let us use this one. X bar plus Y bar into W plus Z. Here pluses are there, let us eliminate. Because NAND means dots only. X bar plus Y bar, you can write XY whole bar into W plus Z. XY whole bar can be written as some variable, let us take it as P. Or you can say XY into whole bar requires one NAND gate is required here. Let us write that output as P. So my answer is PW into Z, P into W plus Z. So what I need to make is PW plus PZ. Take double bar. Then what is the answer? PW plus PZ whole bar is PW bar into PZ bar whole bar. De Morgan's X plus Y whole bar is. Now I am seeing only dots. How many bars are present? Simply tell me. 1, 2, 3. Plus 1 bar is required for P. So 3 plus 1 is how much? 4. So total how many gates are required? 4. Minimum 4 NAND gates are required. Is it clear? Why one extra one is required? To make P. Okay. So this is one way to say the number of 2 input NAND gates required to make any function. Okay, if it is the function is in the form of product term, you can use this shortcut directly bars. If suppose earlier we have done XOR gate, if you remember, I have done A into AB bar dot B into AB bar. Okay, this bar whole bar. This is A XOR B. If you remember, already we have done. In this case, sir, how many gates are required? Don't say 1, 2, 3, 4, 5 gates are required. Please observe, AB is the same here and here also. It is also AB bar, it is also AB bar. Don't count 2 times. We can use the output of gate for 2 inputs, no problem. So AB bar, both are same. So only one time you count. Only 1, 2, 3, 4 gates. I got the same answer earlier also. So here, if the function is written in the product form, you can say based on the number of bars, you can say number of NAND gates required. Okay, copy it. Okay, that is about your implementation of the following functions using your minimum number of NAND gates required. Okay, before going to the next part, let us see the next one in this alternate logic symbols. Let us see that. Keep the side heading alternate logic symbols. Alternate logic symbols. Alternate logic symbols. Alternate logic symbols. Say I have a NAND gate. What is the alternate symbol for the NAND gate? AB whole bar can be written as like this. A bar plus B bar. Both are same or not? De Morgan's law, AB whole bar is the same as A bar plus B bar. Yes or no? You can see here, you may have so you can understand whenever bubble is sent back from this, we can say one logic. Bubble meaning is inverter. Whenever bubble is sent back, then AND gate will become OR gate. Same applicable for OR also. If you have an OR gate, then it is same as bubbled input AND gate. What is the answer? A bar into B bar. A plus B whole bar here, which is A bar into B bar, De Morgan's law. So whenever bubbles are sent back, AND becomes OR becomes AND. Using this, if you want AND gate can be obtained by bubbled input NOR. OR gate can be applied by bubbled input, bubbled input AND gate. Okay, you can check, you can take the inputs A and B, write the function on both the cases, you will match. Otherwise, inversion of NAND is nothing but AND. So take inversion of this, which is this figure, is nothing but AND. Similarly, inversion of both sides, in this case also take inversion OR gate. Take inversion here, it is nothing but OR gate. So these are another way to represent your NAND NOR gates and AND OR gates. Okay, if required, sometimes we'll use this. Practically in the microprocessor chip selection logic of memories, okay, we'll use these kind of symbols. Or for simplifying your logic circuits, I will show with an example later, we can use this kind of symbols also. By sending the bubbles backside, it will make our analysis very easy. Okay. Say for example, let us take one example if you want to see here. So this kind of complex circuit is given. Say I ask you what is F. Okay. First copy up to this. I will show you how to solve this. First copy this. right? See here. Now, if you do normally, forget about that, then how you do p plus q whole bar, this plus this whole bar, this plus this whole bar, and again this plus this whole bar, and this plus this whole bar. It will be make very big equation. We are not able to solve, or it may take more time. Here I will show you easy way. See here. You have NOR gate. Send the bubble backside. NOR will become bubbled input AND gate. You may have the doubt, sir, can I send this one? If you send this, okay, only two bubbles will cancel. But here you observe, if you send like this, what is the advantage? This NOR gate also replaced with bubbled input AND gate. Bubbled means, bubble meaning is inverter. Alternate logic symbols say NOR gates are replaced with bubbled input AND gates. Now two bubbles are side by side. Two bubbles side by side means what? One inverter after another inverter. If you have x bar, whole bar, what is the answer? X. Or you can say it is equivalent to this one. So you can, yes or no, x bar whole bar is again x. So if you give x, you get the x. So you can cancel these two. You can cancel these two, cancel these two, cancel these two for easy analysis. Now what is the answer? P plus Q into R plus S. Here P plus R into Q plus R. Okay. Then you can simplify further here. R plus PQ. Okay. For example, suppose, for example, in the question itself, if it is Q, what happens? P plus Q into R plus Q will come. Then what is the answer? Just for calculation purpose, I am changing. Okay. Q plus PR will come. How Q plus PR, sir? Distributive property. Q plus PR, distributive property. Here also R plus PQ. Now this plus this whole bar. So what is the answer? Q plus PR plus R plus PQ whole bar. You can take here R common. Then what is this? Q plus R into 1 plus B. R. Okay. Otherwise, 1 second. You can take here first and last. You can take Q common. In between, you can take R common. Then what is the answer? Q into 1 plus P. Q. R into 1 plus B. R. So what is the answer? Q plus R whole bar. So for explanation, it may take more time, but exam point of view, just think how many steps you are going. In this complex circuit, first one step, take the bubbles, cancel it, one step, and two steps. Third step, you will get the answer. Yes or no? P plus Q into R plus Q. This one, this one. Add these two whole bar. And what is the answer? Q plus R whole bar. So this is how we solve the, it will, so what is the use of this alternate logic symbols or sending the bubbles back? It will make your analysis easy always. You can observe here. Whenever I send the bubbles back, it will cancel with each other and it will make my analysis easy because two bubbles side by side always cancel with each other. Copy it. Copy the solution first. Okay, see here. That is about your alternate logic symbol. Next, keep the heading two-level logic. Next part, next topic, two-level logic. Two-level logic. Two-level logic. Right. In the two-level logic, let us see the next one. First, in this two-level logic is NAND followed by NAND. What is the meaning of this? If you have a NAND gate, followed by another NAND gate, then this is called as NAND followed by NAND. Then what is the output of this function? From the previous analysis, bubbled input OR gate is nothing but NAND gate. So I can replace this NAND gate with its alternate logic symbol. What is the alternate logic symbol for this? This one. So now what happens? You can understand this bubble, 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 bubble cancels. So what is the answer? After cancelling the bubbles, A, B, C, D. What is the answer? AB plus CD. Okay. So here, very important condition you observe, started with NAND followed by NAND, but what we ended with? AND followed by OR. So what is the important condition we should remember is, whenever you have NAND followed by another NAND, it is same as AND followed by OR. Or if you have any AND OR function, you can blindly replace any AND OR function में every gate with a NAND gate. AND OR function is same as NAND NAND function. So if you have a function of AND followed by OR, you can blindly replace all the gates with NAND gates. Both will give you same answer. Implementation point of view, I am saying. Whenever examiner give you AND OR function like this, x plus y, so xy plus xz, something like that he has given. He asks you how many NAND gates are required. Is it AND OR function or not? Yes, AND OR function. We can replace in this AND OR every gate with a NAND gate. Both will be same. You will get that answer. So how many NAND gates are required in this case? For example, in this function they ask 3 only. So for example, examiner give you AB plus CD, ask you how many NAND gates are required to make it. How many are required? 3 are required. So any AND OR function can be replaced blindly with NAND followed by NAND. Similarly, if you have NOR followed by another NOR, A, B, C, D. Now, NOR gate can be replaced. Alternate logic symbol. What is the alternate logic symbol? Bubbled input AND gate. Now, these bubbles will cancel to each other. So if you give A, B, C, D, what is the answer? A plus B into C plus D. It is nothing but OR followed by AND. Okay. So here what is this? AND followed by OR. Here it is OR followed by AND. So the conclusion is like this. If you have NAND followed by NAND, this is equal to AND followed by OR. If you have NOR followed by NOR, it is equal to OR followed by AND. Or AND OR function is same as NAND NAND. OR AND function is same as NOR NOR. You can copy up to this. Okay. Why it is called two-level logic? Please understand. Here, two levels are there. Gate, whenever your input is given, you will get the output after passing through two gates. That's why it is called two-level. What is one of the advantages? All input signals will pass through equal amount of delay to get the output here. This is called two-level logic. In this two-level logic, other than NAND and NOR, we have another cases also. Next one is NAND followed by NOR. Please observe here what I am doing. You have a NAND gate followed by NOR gate. I am keeping the NAND gate as it is. NOR gate I write it as bubbled input AND gate. Bubbled input AND gate. You understand? Yes or no? NAND followed by NOR. And the NOR can be replaced with bubbled input AND gate. And bubble here, bubble here, bubble here, bubble here cancels. So what is the answer here? Simply AND gate. So A into B into C into D. It is nothing but AND gate followed by another AND gate. Last one, NOR followed by NOR. I am replacing here this NOR with NAND. If it is NOR followed by NAND, then NAND means what? Bubbled input. What is the NAND alternate logic symbol? Bubbled input OR gate. So bubble cancels. So here AND gate will be replaced with OR gate. A plus B plus C plus D. OR followed by OR. So these are the four two-level logics possible. NAND followed by, what is this? NOR. NOR followed by NAND. Here it is AND followed by AND. OR followed by OR. And here, out of the four different two-level logics available, this AND followed by AND, that is NAND NOR logic, is also called as, a name is given, degenerative form. This is the another name for your NAND NOR logic. Which of the following is called degenerative form? Means single term. Here you can observe all has multiple terms. Only NAND NOR is having a single term in the expression A, B, C, D. This is called degenerative form. So NAND NOR expression will give you degenerative form. Copy it. Okay. So these are your two-level logic functions. Okay. NAND, 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 NOR, 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 NAND functions. Okay. Now let us have one question. Implement the function. Write down. Implement the function A plus BC. Implement the function A plus BC. A plus BC using A plus BC using minimum number of minimum number of 2 input NOR gates. Implement the function A plus BC using minimum number of 2 input NOR gates. Right. So here, how will you go for this? Will you take 2 bars and all? Easy way is, see here. A plus BC can be written as A plus B into A plus C. Okay. Now, you see what is this function? OR. Okay. And it is an AND operation of 2 OR functions. We call it as OR AND. So for understanding purpose, we can write A plus B OR gate, A plus C one OR gate, and do AND operation. Then you will get this required function. But you know, OR AND operation is the same as NOR operation. A, B, A, C. A plus B into A plus C. How many gates are required for me? Minimum 3 NOR gates are required. So you can understand here what is the minimum number of gates are required. Only 3 NOR gates are sufficient to make this condition. Okay. So whenever examiner give you OR AND operation, blindly replace OR AND means NOR. No need to do all these things. If you observe, it is a OR AND function, blindly NOR followed by NOR. Similarly, if it is a AND OR function, blindly what is this? NAND followed by NAND. So whenever you are doing any function, previously I have given for implementation of NAND different examples. Now you can conclude. If examiner give you one function, he asks you to implement using minimum number of NAND gate. 3 choices. If it is XOR, XNOR, standard answers I have already given. If it is a product function, bars method you can go. Last way, if it is AND OR function, go by blindly. Any AND OR is blindly NAND. Similarly, any OR AND is blindly NOR. Okay. No need to draw this. If you observe it as a OR AND, if you draw it directly, say how many gates? 3 gates. So 3 NOR. Or directly you can draw this figure also, nothing wrong. In place of OR AND, you can replace it with a NOR followed by NOR. You can copy the solution. Okay, that is about your 2-level logic functions. Okay, in the next class we'll see what are the hazards that are possible. Okay, hazard means the problems that are errors. I will show you in the next class that are possible in your AND OR functions or AND functions and different logic functions. Okay, and what is your sum of products, VOS, and min terms, max terms, all those concepts we'll discuss in the next lecture. Thank you.